All right, thank you guys for coming. It's the last deep dive, end of the whole entire Spark Summit. So thanks for coming out to my session and bypassing anything else that's a little bit cooler. So I'm going to introduce myself and introduce the agenda, and then there's a ton of stuff to cover. So ask questions at the end. If you ask a question, I have 5 Twilio SIM cards to give out, so you guys can enable IoT devices and stuff like that. So real quick, we'll go through the agenda. So basically an intro to the use cases for Spark at Twilio, an intro to who I am, an intro to Twilio as a company. A lot of people in here may or may not know what Twilio is. I'll explain it real quick. And then we're going to kind of deep dive more into like what statistics are. If you guys forgot statistics, statistics are important for trends. And then we're going to kind of go through building a discovery engine. What that means, there's practical code examples. The bit.ly at the bottom of the screen, you can actually download a fully functioning application with unit tests. So you can take it and steal it. It's yours. I don't really care. It's publicly licensed, and you can do whatever you want with it. So we'll do a break, and then we'll kind of go back and kind of deep dive further into why the discovery engine works, what you can do with it, and then how you can hook it up to your ML pipelines and everything else. If we have time for lessons learned, if we have time, I don't have to really go over the lessons learned if we don't have time. If you guys have questions, otherwise I can go into the lessons learned as well. All right, so me, I'm Scott, I'm here. I used to work at Yahoo. I've been doing streaming systems for about 6 years. Started off with Storm. Kind of prior to that, I was working in like the video relay space, working on like GStreamer and some other stuff, which is like kind of syncs and pipe architectures. So like, moving over from Storm to Spark was actually super simple, based off of kind of just like the mental model for how to actually build like a streaming pipeline, what to do with it, which is kind of cool. So worked at Yahoo Games doing recommendations, personalization. If any of you guys do sports bet, I apologize. I did daily fantasy, and I helped actually kind of drive like growth for that, which means that if you like to gamble, we were really good at targeting you guys to gamble more. So that was good and bad. After that, I worked at Flurry, and has anybody here used Flurry? I don't know if it's still around anymore, but it was like the #1 mobile architecture for analytics, and then Google came in and killed it, kind of. But lots of lessons learned there. So stats, data enthusiast, drummer, snowboarder. I make hot sauce, and I'm also like a teacher, and I've been kind of a Spark evangelist at Twilio itself. Cool. So Twilio. Has anybody here heard of Twilio? That's awesome. Have you guys used Twilio for anything? You guys are from Twilio. You're from Twilio. So Twilio itself is a gigantic it's a platform as a service for the communication space. Telecommunications is our bread and butter, but we kind of offer a ton of other different services as well. TaskRouter is kind of like a huge DAG. You can basically just drag stuff around and create really cool, like really difficult like flows. We'll do a bunch of other stuff too. You can take a look at twilio.com to learn more about that. We're also we're a public company, which is kind of cool. All right, so use cases for Spark at Twilio. Almost everybody in here has looked at dashboards. So real-time dashboards and debugging is actually like one of the really, one of the big uses for like streaming in general. So data in, how fast can we get it into a dashboard to see what's actually going on? Fraud detection. In the telephone space, fraud is key. It's really huge. If you catch it, you save millions of dollars. We also take a look at basically carrier behavior, network anomaly detection, going back to the whole dashboards, the streaming ETL metrics aggregations, and then like speech recognition and sentiment analysis. And we do a bunch of other stuff, but there's only so much space on the slide. Cool. So I'm on the Voice Insights team at Twilio. We basically have a service that allows our customers to take a look at everything that's going on within their own account within the voice space for all of their programmable voice services. Given that we have an API, it's really nice for people to be able to see what's going on. We process around 3 terabytes a day, 4 billion raw events, 2 billion metric and session aggregations daily. We're storing about 40 terabytes a month just for our own data. For the Voice Insights team, we're a team of 6 people. We have a ton of data, and the telephone space in general produces a ton of data. So yeah, basically powers a bunch of dashboards, customer support, carrier operations. Pretty much the data is widely used everywhere within our company. All right, so let's go through the streaming architecture. Everyone's probably seen way too many pipelines, but here's another pipeline. So here's basically what we do on our team. This is also something you guys can easily reuse. So don't just have Kafka, and don't just let anybody enqueue things into Kafka, and then hope for the best later on in life. That's really difficult if you don't actually have like a structure to your data. So one of the things that I recommend that's actually worked out really well for our team is to basically front everything with an API. You have a single point of ingestion, you have a single point of failure, but you can spread out and mitigate those failures. So the API is basically going to sit there and it's going to validate all your data. It's going to authenticate the user. It's going to authorize insert into specific topics. And then it also allows you to basically take like a simple format like a JSON object and actually pass it through like a protobuf encoder, an Avro encoder, and then you can dump it into a Kafka topic, but you don't have to worry about saying, okay, I hope you have the right version of our jar in your client library. If you don't, then the data is going to be you're going to have to sit there and see how do you merge it later on, and that can be really, really difficult. So if you have an API, then you know what's coming in. You can also do like schema evolution as new events come in, just without people having to actually update most of their downstream APIs. So green is Kafka and/or other pipes. It could be message queues. It doesn't really matter. In our case, it's Kafka. In a lot of other people's cases, it's probably also Kafka. So API in to raw events. Raw events are actually pre-processed to basically consolidate everything on the screen. I've skipped that part. But basically, raw events come in, pre-aggregation, and then everything kind of goes into our streaming aggregation pipeline. Then afterwards, we kind of just basically take data, chuck it to another topic, it gets picked up by another app, and it's basically just like relay with data. So in the same way that you send packets back and forth, do it with Spark apps. Makes it really easy to actually recover and replay your data. It works out really well. So this is actually what we're going to go through today is basically building a discovery engine. We're going to skip over the API. We're going to basically show what the raw events look like, how to aggregate it, how to create windowed metric aggregations, and take a look at a bunch of different ways of actually windowing and aggregating data. We're not going to talk about like Elastic or Redis or S3. There's ways of easily storing your data. You can put it in HDFS. We're not going to cover that part, but we're going to showcase basically everything else. And then the trend processing and what you do with the data is going to be theoretical, and it's basically a homework assignment for you guys if you want to do it. Otherwise, you can also just plug it into your ML pipeline. We're just creating data, and the data is statistical data, which could be used for literally anything you're doing. In this case, we're going to do it for the telephony space. All right, so before getting into how to do anything in Spark, I just want to kind of briefly go over some kind of key values for what's quality data. And basically, it needs structure. JSON is good, and I know there's a lot of stuff like Cloudera is working on an unstructured ML on random data, and that's cool. The stuff that we're doing in our pipelines are stuff that's in our data lake. It can't just be kind of ad hoc random JSON. If it's ad hoc random JSON, it's like it's a Java object. You have no idea what's there, you don't know how deep it goes, and you hope for the best. 2 years down the line, the person who actually wrote the API to actually add that data to the data lake might not even be at the company, no one knows what to do with the data, you throw it away. So you basically spend the money to store it and throw it away later. It's kind of stupid. So no JSON, unless you have another reason for it. And that reason would be if you basically own a producer and a consumer and no one else is going to touch it. Then do whatever you want, have POJOs, have everything else, use Jackson, it's all good. Instead, use Avro, Protobuf, or Parquet directly, because you can actually have a schema, you can version the schema, and then everyone knows what to use, which is really cool. You can even have jars and everyone can share that jar, which is nice. I'm not going to talk about Avro or Parquet. We'll talk about Protobuf today, just because it supports backwards compatibility really easily if you do the right thing. So before kind of moving on again, we're going to talk more about establishing a data contract. So data contracts are really, really important. This kind of goes back to the principles of no JSON. If you know what the data looks like and you know what's valid, then you can actually trust your data. Who in here is a data scientist? Yay. How many times do you fight with people over what the data looks like? Yay. Everyone does that. No one knows what the data looks like, except for the first team to actually enqueue the data or produce the data. So have a contract, have it documented, and then ensure that you're not going to actually break backwards compatibility. In the case of schemas that are hard to evolve, like Avro, don't ever go from a null type to a default type. It breaks backwards compatibility, and then you actually have to evolve the schema itself. So more kind of just food for thought. Aside from that, data should be easily flattened. If you have seen JSON or any other kind of structured data where it basically just kind of traverses the entire screen, that's cool, but it's really hard to work with, and it's hard to actually create like an actual flattened row from that data. A lot of times you'll have a namespace collision or something else with the actual like deep data, which is really hard to kind of propagate back up again. So ensure that you don't go too deep, and it's a good kind of thing to live by. So final thoughts, structured data allows for compile time guarantees, write once, compile across languages depending on the library. And then it also, the nice thing too about like most of these modern data structure languages is that you actually don't have to worry about using just like a Java serializer. A lot of them actually come and ship with their own kind of parsers. So non-Java object serialization is really good for Spark. If anybody has ever stored something in a session in Spark, broke the serial version UID, and then tried to actually replay from last checkpoints or whatever else, your app dies. So make sure that your data is not corrupt. It's a really kind of good lesson to live by. The other nice thing too is that with that external serialization, it just helps with like actually, so taking a step back for a sec, given that we're talking about streaming applications, it's not a batch. We can't just start it back up again. We can, but it's a lot harder because we're expecting, a certain kind of contract. Like for our team, we basically process within 250 milliseconds. If we decide we're going to basically stop for just a little bit, go back, update our code, push it back through our whole entire release system again, we might have basically 2, 3 hours, 4 hours worth of data in our backlog. At the same time, all of our downstream customers are offline. Anomaly alerts, other monitors, metrics, everything else is gone. So it's a huge outage, we get paged, and that sucks. So external serialization and everything else will actually help you like with your deploys. So you can have an app running, you want to have a new version running, maybe you want to canary it. It can pick up from the last checkpoints and just start running on its own. So you can basically have 2 applications running side by side, and at a certain point you can basically shut off the old one, and you don't have to ever worry about it. So it's been really easy for us. Like we can do deploys now where it's a rolling deploy of a streaming application, and we just go home, or we go out to lunch, it doesn't really matter. Unit tests help there too. Cool, check the time real quick. Awesome. So we're going to talk just a little bit about percentiles and histograms. For anybody who hasn't thought about statistics or calculus or anything else in a long time, there's fun pictures and it makes it really easy. So what's a percentile? Percentile is a group of numeric observations. That's it. So we have a set of data. Data splits are really important for helping kind of shape the look and feel of a specific set of numeric data. This is leading towards histograms. So split points help us basically bucket frequencies of data inside of a set of numeric data. So common split points, if you've ever taken a look at like, if you guys have used R or anything else, or you'll have basically a summary. So you basically have a min, you have a 25th percentile, a median, 75th percentile, and then you have your max value. So it's easy to kind of split that data. Histograms are bucketed distributions of numeric data sets. A lot of times people talk about distributions, they talk about a normal distribution. Normal distribution has the area under a curve. Everything is kind of nicely under the curve. And histograms in general allow us to understand the shape of our distribution of data. All this is going to make sense in just a second. I'm not just going off on a limb, hopefully. One other thing too that's kind of neat, if you know about normal distributions, is the 68, 95, 99.7 rule. So basically 68% of all your data is within 1 standard deviation of your mean. And the rest of the data is within 2 or 3. Yay. All right, cool. So now that we know about percentiles, we know about histograms, we know what the shape of a distribution looks like, we can start talking about time series histogram analysis. This stuff is really, really cool because if you're trying to do any kind of statistical like inference, it's really nice to know what things looked like so you can compare it against what things look like now. So the ability to basically look back over historic trends of histograms also helps you with MP completeness because you literally look at a very, very accurate distribution of what things were without having to actually go back to all the raw data. So you can actually throw away raw data if you trust yourself, Otherwise, you can just look at the histograms and you can kind of speed up different observations as well. All right, cool. So this is going to now start the code part of this whole entire discussion. So quantiles and histograms in Spark. Has anyone in the room ever created a quantile or a histogram in Spark? Yay. Thank you, guys. Are you doing it with data frames, or are you doing it with data sets, and is it streaming or is it batch? Okay, and is it batch mode or streaming? Okay, cool. So you know there's some kind of difficulty in basically kind of extracting that data if you want to merge it. So if you're trying to create like a windowed aggregation, it can be a little bit harder to take those quantiles, unless you're really, really good at math, to be able to kind of merge all that stuff back in. So I kind of show what's available, and kind of two different forms of kind of the same thing. So with data frames, you have a stat subobject, and that has an approximate quantile. So this is like a hyperlog type sketch, where it's not necessarily having to look at all the data to be like 99.9% accurate in representing what the data looks like. So it's actually it's cost effective in terms of like the overall memory. Prior to data frames, you had the RDDs. RDDs are a little bit harder to work with because you might have an RDD that encapsulates an event. The event, you might want to take a look at a histogram of just a single value, so then you have to map down to the value to create basically an RDD stream of just doubles. And from there, you can basically gain access to the histogram function, which will automatically bin stuff, and then you have to basically propagate everything back up again. So it's a little bit harder to work with. In Spark 2, I think this is available beforehand as well, but you have the ability to basically access these mutable aggregation buffers. So what a mutable aggregation buffer does is allow you to basically extend the aggregate functions that you have on a data frame. There's pros and cons to using the mutable aggregation buffer, but this abstract class is basically like a class that we wrote on my team that kind of encapsulates a kind of general use case, and then it's easy to kind of override that and do whatever else you want with it. And I'm not going to go too much into like product types. If you used Scala before, product type is kind of the unit of case classes. And then from there, who here knows about expression encoding? Awesome. So expression encoding is the way that Catalyst ends up serializing data. So if you have an unstructured row, that row is actually stored as kind of a buffer. And if you're going to pass the buffer back and forth and kind of convert it back into a data frame, it needs to know what the buffer looked like. It needs to know what the actual schema was. So what are the struct types that make up this individual row of data? Yay. Now you guys know a little bit more about expression encoding. In the downloadable content in Git, there's a really cool example of how to actually expression encode protobuf into an actual struct. So you can use protobuf and do everything you'd want in a data set. Data frame, doesn't matter. It's now not just kind of this foreign entity within Spark. Cool. So going back to basically the aggregations themselves. So the upside to actually using mutable aggregation buffers and the regular just kind of the unstructured rows from the data frame API is that it's human readable. If you take a look at this guy right here, you say, okay, cool, we have a call event, it's grouped by ID, we have some sort of sliding window, now we want to take a look at PDD. That's something that's probably foreign to everyone in the room. PDD is post-dial delay. If you've ever heard a ringing tone when you've called somebody, the time you waited before ringing is post-dial delay. It's a PDD value. So this kind of shows you the way that we have done statistics and stuff in the past using just the data frames API. And then adding like a histogram aggregation on the PDD on the PDD value itself. I don't have a good word right now, words are hard. But so the PDD value, we basically pull out and we alias it as a histogram. And from the histogram, we can basically take a look at kind of a substructure. I'm going to go into a little bit more into that in a second. The downside to this, unless you're really, really smart, again, everything kind of goes back to smartness. If you're taking a look at an individual value and you're doing a streaming aggregation over time, and you can't easily do like a binary merge, then you're going to be continuously kind of updating your data, and you have to store a really good representation of what your data looks like. All values, unless you're using like a sketching library. And so I'm going to go into sketches in just a second, because we use sketches to solve this problem, because other people are better at math than I am. So the performance and the control. What I mean by control, if you take a data frame and you do a group by on a data frame, you then have a grouped relation. A grouped relation allows you to basically do an aggregate, you can do a count, you can do a sum, but you can't actually get back into the state unless you're to basically go down to the RDD level. So it kind of, you don't really have the APIs that you want if you're trying to do like introspection. Say you want to add monitoring, say you want to basically emit like the serialized size of something, you really can't unless you override that stuff and put it into like a mutable aggregation buffer, or if you move into basically the data sets API. So this is basically kind of final thoughts on the aggregations. We tried a lot of different things, and we had an application running for about 6 months that was just using mutable aggregation buffers. It was using the windowing functions, and it was great. But there was a lack of kind of control for what we wanted, not necessarily because we didn't try hard to add the control, but because there wasn't enough of an API there. This is prior to Spark 2.2, and Spark 2.2 gave us flat map groups with state. And I'm going to go in a little bit more into that in just a second as well, because it really gives you the full functionality. If anyone's ever used like a map with state, flat map groups with state's much better because you can actually time out an individual group versus having to time out everything. It also adds event time timeouts. So if you were to replay like 3 days worth of data, you don't have to wait for 3 days to actually have things time out. You can actually just fly through it as fast as you possibly can and just re-aggregate everything else. So event time is better than real time for replay. Cool. Let's see. So is there any questions at this point? And if there's not, that's great, because I can just kind of keep on going because there's a lot of content. Yes? So protobuf was better for backwards compatibility. With Avro, if you haven't, so there's a couple answers here. So with Avro itself, if you have a flat structure, it's really easy to upgrade the flat structure. If you're trying to basically use modular reuse in Avro, and you have a subtype, so you have like a nested structure, the inner structure itself, if you just change the inner structure, and the outer structure doesn't understand, you get an index out of bounds exception, because it doesn't understand that only the inner object actually mutated. So unless you're using like a Confluence library or Confluence server to basically like scale up the Avro, or if you're using like a Kafka Connect and things like that, it's a lot harder to actually do that. So with protobuf, you actually have like the binary splits for the actual data itself. So it's like, okay, this is a long value, this is a string, this is a sub message, so we know that something else is going to exist. That's really, really nice because you don't ever have to worry about an array index out of bounds exception. The other problem you have is an end of wire exception if you screw up the actual protobuf or if you delete a field that did exist in an earlier version. So you can screw, like, basically we can screw up a lot of things. We're engineers, we do that all the time. So we break stuff and then we fix it. But it's really hard if you corrupt an entire data set to be able to try and go back and say, okay, I need to fix everything right now. So it's better to do it the right way or understand like what you're using kind of beforehand. So that's kind of a twofold answer. But I also, I came from Yahoo, and Yahoo, we used Avro a lot, but we also used protobuf a lot. And protobuf had some really, really cool contracts, and we all kind of just learned to love it. It's also kind of cool too. I'm going to show you a trick with protobuf in just a sec as well, as we kind of go more into like how to use flat map groups with state and how to use the actual data set API. Cool. So I don't know what time it's supposed to be. So we're supposed to take the break. When is the break? It's at 4:50. When is it? Sorry. We don't have to take a break. We can take a break whenever. If you guys don't want to take breaks, we don't have to. I think I'm luckily kind of moving faster through the slides than I thought I should. So pretend it doesn't say next up after the break, and we'll just kind of go into building the discovery engine itself. This is why you guys all came here. So to get into what we want to, how we actually want to solve a problem, talk more about the telephony space. So first off, thesis. Global telephony is hard. So we have tons and tons of servers all across the world, and we're running on Amazon, and we also have other people running on Amazon in their own networks. You have underwater fiber lines that get cut all the time. Servers can go up and down at any given point. People can lie about the state of certain services. So anybody's heard of T-Mobile's ringing issue? T-Mobile got fined $40 million for basically faking ringing. So for a lot of the stats we capture for certain carriers, we basically have to trust the data that's coming in. It kind of goes back to the whole data contract. So if you trust the data that's coming in from a carrier, from a different a service provider, then you can use that data to basically kind of tune your different systems. But if someone's lying about that, then there's nothing you can really do with that. So global telephony is hard. So if you're just connecting two endpoints globally, it's very difficult depending on whether or not you actually have metrics for every single hop, and you actually have an entire graph that can kind of route around issues. So given networks can go down, then how do you connect 2 points? So we should build a system to auto-discover trends in real time for our key performance metrics and automatically report them. So cool. So now we're going back to the initial kind of slide about what this architecture looks like. What we're going to do is actually define the structured streaming application to ingest our raw events, aggregate them, and then basically just pipe the stuff back to Kafka again. If you use Kafka Streams, this is why Kafka Streams exists. It's data in, do something, data back out. Cool. So in order for us to actually create our engine, there's a couple of things that we have to go through first. So this is more of kind of like the hands-on approach. I come from the hands-on kind of training space. If anyone's ever been to the Hacker Dojo in Mountain View, I did a lot of training there, which is really fun. So going back to our thesis problem where we wanted to actually detect if a carrier goes down, we basically say, okay, we're going to have an event stream. Inside that event stream, we're actually looking for post-dial delay. So PDD, which we talked about just a little bit earlier. So PDD, again, is basically the time it takes for a service provider or carrier to actually send back a ringing tone. If you've ever called somebody and it takes 20 seconds for ringing, you probably have hung up because you think that something's broken. And typically it usually is. So PDD is actually one of the key performance metrics that we use to actually rate a vendor. So if we just take a look at PDD, because otherwise we'd be here for the next year talking about the other metrics we also look at, this is one of the easiest ones to kind of encapsulate and understand and build a mental model around. So we're going to define an actual call event. So a call event, we have event time. If anybody has ever accepted data from a third party, then you understand that time is hard. Time is very hard. So if somebody marks something as UTC, it may or may not be UTC. So one of the things that I learned at Yahoo and from their whole entire data highway was to basically take the event, don't necessarily trust it, but log it. So what's the epoch time when we received it? Because that's that's your authority saying, yeah, we got this. So you can actually also measure like latency. You can do lag time from the time that event was actually created to the time that you actually received the event. If you trust the producer of said event and you're receiving it late, then that's a nice metric for you to actually page off of. This downstream API is taking way too long to actually send events. Let's make sure that the other pipelines don't slow down. So one of the other issues too with like massively parallel pipeline architectures is that a slowdown in a single pipe can trickle down. It's a huge butterfly effect down to every single downstream service. So if all downstream services can't actually keep up, then you have a huge bottleneck, and then your whole entire system can go down, and then you're out of a job. So event time, logged event time, event ID. So event ID, we're going to go through all this stuff a little bit more in just a sec, but for Kafka, you should partition. An event ID can be used for partitioning. Event IDs can also be used literally for item potency. So you can say, okay, we've already got it. Let's deduplicate it. Spark and Spark, I think it was Spark 2.2, gave you the ability to basically do deduplication on an actual stream of events. So if you can reuse the same ID for a bunch of things, then you can actually save on the overhead of the actual events. So use that. Then the other stuff here we have is basically route ID. So before we had a nice diagram of basically a bunch of different hops from different points of presence across the globe. So a route ID might encapsulate basically a source and a destination. And you don't want to actually say, hey, we traversed a bunch of stuff in between. You just want to basically say, I want to identify it as a route. And that way, you know whether or not the route is healthy for a specific set of dimensions, for a specific subset of events. So going back through here, brownie points if you can be reused for deduplication. The other thing, so we're going to talk a little bit more about protobuf in just a sec, but the nice thing is that protobuf, it's very easy to actually take your data and put it to a byte array. If everything outside of your statistics is the same within a category, then it becomes a really, really strong grouping key if you've defined that well. So we're going to talk a little bit about dimensional hashing so that you can look up a single record to get a set of 20, 30, 40 dimensions. Consider this also a feature for any of your ML. So a dimension is a feature, a segment, depending on who you talk to. If you think about like the data warehousing toolkit and stuff, then there's other nomenclature for all this stuff. But for this talk itself, we basically have metrics and dimensions. So here's a subset, and this is, just to be super verbose, here's a signaling event. Signaling event encapsulates basically a pre-flight event, which is connecting 2 points and waiting for ringing. A signaling event, we also have call states and other stuff we can piggyback on the same data object, but yeah, in this case, we're just gonna look at PDD. So this is not just here to say, here's what the event could look like. This is here to basically show how you could actually do event evolution within the actual like frame of a specific event. If you've ever had to do joins on multiple Kafka topics, and a topic goes offline for a little bit because a broker has a lot of I/O on the producer side or the consumer side, then you're basically awaiting data for a long time. If you ever use the RDD framework and you're trying to do a join RDD and you have no data on one side, you might not have any data because it's going to go, I don't know what to do. I can't zip this. So there's a lot of problems with many, many, many different topics kind of getting aggregated into the same pipeline. So for simplicity, you can put it all into the same pipeline as long as you know that the rate of production for specific events is going to be similar. Otherwise, you can have kind of a hotspot with a single event, and then you're having to await a lot longer for data to show up. Also enum ordinals can be used in your ML jobs. You don't have to worry about string encoding. So you have labeled data, but now it's also numeric type, which is great. It also is really, really good for the serialized size of your records. You're not repeating strings over and over and over again. So it's good for kind of saving money, which is great for everyone's companies. Cool. So kind of moving on, this is the metric aggregation that we're actually going to create. So this kind of shows you, it's not necessarily completely flattened, but it kind of gives you an idea of what we're trying to achieve in this discovery engine. So we have a metric. The metric could be anything. There's a window start, a window end, and there's also a window interval. You have a certain number of samples. It could be a total set. It could be a subset. There's statistics. There's a histogram. We've got dimensions, and then a dimensional hash. I'll talk about the dimensional hash a little bit more in just a sec. But kind of going back to the how do we group stuff together into a strong binary grouping key. Take everything that won't change just based on samples, stats, and your histogram values, but then use all of that stuff as a grouping hash. And then here's just a really quick example of a simple way of generating a strong hash, and also using the libraries that ship with Spark. So murmur hash, yay. Base 64 URL encoding, cool. This is all from Guava, no extra libraries. You have a small, jar size, cool. Provided by Spark, cool. So now we're going to kind of put everything together. So this is kind of why we just went through the whole kind of history lesson on percentiles, histograms, and everything else. It's kind of leading up to this right here. So building a discovery engine that's statistical time series histogram analysis. So everyone's familiar with a run loop. There's also a main loop, which can power all of this. I'm showing kind of key pieces of code from the source code that's on that bit.ly at the bottom of every single one of these slides. If you guys want to take a look at it as well, again, you can steal it. It's completely, it's completely licensed for theft. So use it however you want. Cool. So what are we doing here? We're going to create an event aggregation. We're going to feed it a config. We want to then process our data. Read Kafka stream. All it's doing is basically creating a Kafka stream reader instance. And we're not going to go into the actual configurations, but that's also in the take-home application as well. So create a stream. Implicitly inject Spark in there. This is really good for reuse when you're actually unit testing. Implicits are awesome. If you don't know what implicits are, they're really cool. If you've ever used like a different dependency injection libraries, then you understand like why dependency injection is cool. And an implicit is basically saying at runtime, I'm I want to figure out how you want to inject. So am I going to bubble up to an actual companion object? Or are you going to provide this explicitly, or is this going to be implicitly actually associated with a specific method? So processing the Kafka stream with our Spark session. Now all we're doing is writing it. Our query name helps us actually query, and/or if we're monitoring these streams, we know which stream actually died. Most companies aren't going to have a single streaming query for a single job, so not necessarily having a random ID is really good to monitor. So monitor your queries. And then also have everything else be config driven, because it's really easy to basically start your app back up. You can start things back up in recovery mode. Doesn't really matter as long as you can completely drive this from configurations. It really, really helps after an outage or during an outage. If you have everything kind of compiled down and all the configuration is sitting in your resources directory, then you have to compile a new jar, you have to ship a new jar, you have to hope for the best. But if you can literally monkey patch on a server, because things are going bad right now, it's really nice to be able to just literally stop the process, monkey patch, start the process. You might be down for 30 seconds or less. So configs are cool. All right, so we have this basically event aggregation config process. So here's the process method. It's taking a data frame. The data frame itself, in this case, is a Kafka data frame. We've implicitly injected Spark session. What we want to do is basically return a data set that is metric aggregation. The cool thing here is that the metric aggregation is actually protobuf, which isn't supported by Spark. But here it is, which is cool. And there is the whole entire expression encoder in the source code as well. It's too long to fit on a slide. But it's really cool. If anyone here, who's ever done code generation dynamically at runtime? Yay. And everybody else here who's using Spark has also done it too. So Catalyst Optimizer does code gen for you. And if you want to actually extend the Catalyst engine, it's really easy to do so if you understand how to use Scala to write Java. So it's actually not as easy as it looks. But that's neither here nor there. So here we go. So basically we want to process our data. We want to have, and basically, so we need different encoders to be able to actually ship data back and forth. So the expression encoder for metric aggregation is just doing that. So if we want to be able to serialize protobuf from the driver to the workers and from each of the individual executors kind of across the board, we need a way of actually easily doing so. So the expression encoder will allow us to basically extend at runtime, like implicitly, the actual way, the way of basically extracting the encoder for an individual row. We're also, if anyone's ever watched the talk on structured streaming, there's a watermark. So typically, you don't want to just have an embedded table that's kind of just continuing to fill up more and more and more disk. You usually want to have it bounded. So like in the call use case, we usually await a certain number of hours after a call for kind of close of books. So close of books could be your watermark interval, as long as you can store it all in the actual process itself. In memory or on disk. Facebook had a really good talk yesterday on shuffling. And if you can't keep everything in memory and you can't keep it all on disk, then you have to actually do some things a little bit differently. So you guys should check out the SOS. So watermark interval allows us to basically say at a certain point we want to reject any more records from actually being added to this unbounded table. And so from there, we're going to basically take our data frame. We're using map partitions instead of just maps, so we can actually take the iterator and do everything on the actual executor itself. Versus, there's another talk as well about basically the difference between maps using UDFs or actually doing like a map by map partitions. Map partitions works really, really effectively. If there's anything else you also want to do, say you want to basically do timing. If you want to time how long it takes to do a process on an individual executor, if you're just using map, you can't actually access that. So if you're going to have an iterator that's going to be, say, fetching data from Redis, fetching something from Elasticsearch, doing anything else, and you want to actually time that for metrics purposes, that's a really great place to do that. Cool. And then once everything has been converted into our metric row, we're basically grouping the metrics, we're watermarking the metrics. Our group key is now our binary data from before. So we had this guy. So our binary data is now our actual group by key. So what we're going to be doing now is doing a flat map groups of state on our binary protobuf. So the trick here is that we don't have to actually assume any extra resource overhead to actually get back to what the format of the data was. All we have to do is basically take all of our metrics. This goes back to PDD. Take the entire metric stream, which is an iterator of metrics, and just literally do a data sketch. So we're going to basically store a representation. If you guys are familiar with hyperlog, we're taking just a sketch of the data, and then we're going to store that as our group state. So our group state is going to be an array of bytes. Our input is bytes. Our key is byte. And everything is pretty much bytes. So this is a really good way of kind of pumping tons and tons and tons of extra performance out of your actual flat maps groups of state job, because you don't actually have to figure out how to actually kind of query the rest of the data. You're using your key, which is also your final state, which is neat. So what I just said is basically this slide. So metric aggregator, the key is the metric aggregation. We're iterating over product metric, which basically keeps our PDD metric, and then we're going to group it, and then at the very end, once we've actually hit our watermark and we've actually timed out, we're going to return an iterator of our metric aggregation, and that's going to actually basically go back to Kafka again. So here's just kind of a very nice example of what's actually happening in like the heart of the flat maps groups of state. So you have state. State is actually stored in a StateStore. So it can be backed by HDFS, it can be backed by S3A. As long as it's HDFS compatible, the state can be stored there. This is nice if you're on Amazon, like we are. Amazon plays Russian roulette with boxes from time to time. So if your driver, your executors are randomly taken offline, then you don't have to worry about actually recovering a ton of other state itself. So always checkpoint. Don't actually put it to a temporary file on an actual machine unless you trust the hardware. So here we go. So we get our state. State may or may not exist. If we had some state, all we're doing is basically taking the last data sketch, a current data sketch, and I have more on data sketches in just a second. And then we're just creating a union sketch, which is going to merge all our data back together. The point of this is so we can actually create our quantiles and actually create the individual histogram values themselves. But all we actually have to store is a byte array. So if you haven't used data sketches before, there's a library used a lot at Yahoo, and it actually works really well. The 2-byte array with true is compaction. So you can have compact byte arrays, which is really nice, and then everything is just stored in buffers. So it's pretty nice. In the case where we actually don't have an individual value, we can pull out of the StateStore. We just build a new double sketch. So builder set k for k points. I'm not going to go too much into K. You guys can take a look at the documentation and data sketches themselves. But just think about, say, there's a bunch of different points. Those points have frequencies. As more data comes in and frequencies change, those points might move around a little bit. But you're basically storing a certain number of values for a representation of an entire data set. So it's been benchmarked via the actual data sketches library that like 34 kilobytes can actually store about a gig worth of data. So I don't know, it's better to store kilobytes than gigs in my mind. Plus it's fully mergeable. You can union it and you don't have to really worry about it. And it's basically binary at that point. So in the flat map groups of state, the state itself, you can update your state. So at the very bottom of this method, we update our state with our metric data. Afterwards, we set a timeout on our data because we eventually want to time out and emit these records. So if you have a window of 5 minutes and you've got a watermark of 5 minutes, in 10 minutes, you're going to emit a record. So otherwise, you'll have basically unbounded data that's never emitted, so you're just aggregating indefinitely. So don't aggregate indefinitely, aggregate and emit data that you actually want to do something with. That's pretty much it for that part. So this kind of goes back into the data sketches themselves. So data sketches, if you search online, go into Google, data sketches is easy to find. There's a GitHub IO page that actually shows full documentation. There's Java examples, there's PIG UDF examples. There's everything you'd ever need to kind of move along and start using data sketches. We use it in production, which is cool. So it's not like a little kind of pet project or anything else. If you don't want to use data sketches because it's a Yahoo library, there's also AlgeBird from Twitter, which is actually a really good library for doing statistics as well. Everything kind of has the same sort of things, like min-max counters and things like that, and other ways of doing quantiles or frequency sketches. It's always very lightweight and kind of easy to use. So I won't go too much more into the actual data sketches themselves, but basically, at the end of the day, data sketches are nice, it's friendly on Spark, and you don't have to really worry about Java out-of-memory exceptions because they're super lightweight. Hold on. All right, cool. So moving on to testing. So what we've covered so far is basically creating a pipeline, processing data from Kafka, actually applying a windowed, watermarked aggregation on that data. Let me just go back to this while I talk about it. There we go. So this is our stream. And the stream is really nice, but if we want to be up and running 24/7, 365, we also need to be able to test it. Testing in Spark, there's a lot of good libraries. So Holden has a really good library that you can use, and it's also part of this library as well, that actually allows you to basically have primitives. It's very easy to use like JUnit or anything else, or just Scala test, to be able to actually create a Spark context, or create a Spark SQL context, use a Spark session, and then actually use that inside of each of your individual tests. And that's part of the library. And I'll actually show the test in just a sec as well. So here it is. So we should aggregate call events. So we have a configuration. I'll go into this in a little bit more detail, but we're also running embedded Kafka. You don't have to run embedded Kafka. You can use memory streams as well. So a memory source will allow you to actually create a source of streaming data in your unit tests as well. One of the problems we've had in the past with either kind of like mock data and or different kind of mock environments is that sometimes it bites you on the first release. So if you can test using the same embedded data or the same embedded kind of framework, like I want to embed Kafka, but I don't want to basically test that using just basically like some kind of parallelized map. Let's actually use Kafka if it's cheap enough to do so. We haven't seen this actually bite us. Like for a lot of times, it's basically like, I want to do an aggregation. So say if you think about like an ETL, you're going to have data. It's going to hit a data source. At the end of the day, you're going to basically emit a certain record. That's pretty easy to do. And you can kind of back it by saying, here's a scenario for here's a scenario. I'll go into that in just a sec as well. But say you have a stream of JSON that can be converted into Avro or protobuf. You can actually inject that into your test. And you're testing with real live data and or like redacted because you don't want to have GDPR issues in your unit test or sitting in GitHub, but anonymized data that's actually real world data that you're testing off of. So now you can do that. So I have a scenario. So we have this test helper that loads a scenario, basically casts it to a protobuf call event from a path of JSON. Then we create an iterator. You see test utils, create topic. We actually create a topic. And it's actually really lightweight. It takes like a couple seconds. It isn't so bad. When you're running it in Jenkins, you don't have to actually think about it. We then take our scenario, and we basically send messages to Kafka, like somebody else would be producing in the real world. And then all we do is actually create our application. And the whole entire app itself has been basically decomposed so that it's actually good for testing. One of the hardest parts is basically patterns for testing in almost any framework. It's, especially like in like any kind of pipeline infrastructure or like even Spark itself, it can be really hard to actually test what you're doing. So you can test literally like a single kind of sub-process, but if you want to kind of test end to end, a lot of times you're using like, you're using different like Mockito classes or you're using like WireMock or something else, which is kind of really cumbersome for actually setting up an individual test. So if you can just embed something that's easy to work with, and you don't have to mock it, just embed it, it's actually a lot easier. So we have something called Kafka-backed test, which allows you to basically override what's in the test for Kafka, and then you can literally just write messages, which is nice. So we basically process the app. We create a stream. We put it to memory, so format memory, which is only pretty much used for testing. If you do it in production, you're going to run out of memory. Our output mode itself is flexible. So in the test itself, if we feed this a different configuration, we could test append mode, we could test basically complete mode, update mode. If you're not familiar with structured streaming, there's output modes. And those output modes itself basically say, in the case of complete, it's every record that comes through and all the state, just keep on outputting it. If you want to update, it's only the rows that have been updated. And if it's append, then it's only the data that is basically been chucked from the state machine. So it's, you've basically hit your timeout, you've hit your watermark, and now your data is fully emitted. So that's where like the exactly once contract comes from. is the ability to basically just push down once. So append mode is nice if you want to do something that's kind of more accurate. So like for these aggregations and the statistical aggregations themselves, we can use append mode so that we actually trust that we've closed books and that our data is complete and that the data representation is actually what we want it to be. If it's update, then we have to worry about merging and or writing over the same data over and over again, which is painful because going back to the beginning, you have a data contract and you want to actually have valid data. So if you don't know if it's valid, then you throw it away and you start over. Cool. So that itself is basically how we test. Yay. This is really, really small. I'm just going to run this. And that broke, because live demos always break. Yay, awesome. I don't know what I broke, but I also have the output already stored on my desktop somewhere. Yay, all right. So had I not broken this because I was updating the slides before this demo, then you would basically have this. So this also doesn't look well, it doesn't look good on the screen. But, so what we have here is basically every single update. So we have a number of records, we're updating the timeout, we have a group hash key, we're recovering last state, we're merging, we're updating, and you basically kind of continue that flow over and over and over and over again. And then we're basically saying, I want to take a look. So I'll just open this back up for a second. So we want to take a look at the schema. So given we're using a memory table is actually the same thing as saying, I want to create a temporary view. It's the same thing. So memory table allows you to basically query the data that's been output in your query. So we say, oh, okay, we created these call event aggregations. I now want to select everything from the aggregations and look at the schema. So I'm glad I have this because this is what the schema looks like. So we looked at the protobuf before. So we had metric, window start, window end, window interval, samples, stats, which has our entire statistical structure, min, P25, median, P75, 90, 95, 99, max, mean, standard deviation, variance, pretty much everything data science would ever want. And then also the histogram to kind of show what the shape of that data looked like. So if you want to, like we're going to talk about in just a second, and then I'm going to probably run out of time after that, but so we have our stats, we have our histogram, we have our dimensions, then we have our dimensional hash. If you take a look at the bottom right, we have a dimensional hash that's never going to change. Right now we're only looking at PDD, but say for example we're taking a look at packet loss percentages. Say we're looking at any other kind of data that's a key performance metric. It's very easy for us to say, basically group by dimensional hash, and now we can take a look at how all the covariance of all the data actually looks together. Without having to say, okay, select where this entire group of dimensions and shit, I forgot what I'm doing, just have a hash. It makes it super easy. So you can then do a query where you're like, okay, here we go. Select average stats P99 from call event ags. That feels right, it feels easy. So by being able to actually have your sub-statistics, it's actually easier to do averages and anything else than it is to actually roll up quantiles in real time. So if you can just do an average of a statistic that's already kind of pre-composed, then all you're doing right here is basically saying, we want to basically have a streaming OLAP engine. So discovery engine itself is basically a way of kind of emitting kind of pre-composed statistical descriptions of individual metrics. Cool. So I'm going to go back to the slides real quick. I'm going to pick this back up. So I'll update the code. Anybody who downloaded it, I'll update it to actually have it work so that you guys can actually see the tests working if you want to later on. Otherwise, the tests do work, and I think I changed like one line of something. So here's basically step 2. So now that we have we've talked about the API, we've talked about the raw events, we've taken a look at what the events look like, we've understood a little bit more about what protobuf can do or what Avro or Parquet can do for us. In this case, I was showing the protobuf example. We showed how to basically window the data, aggregate the data, and then actually output the data. So now we know that we can output streaming metrics, and then we can enqueue that into Kafka. Once it's in Kafka, we can then pick it back up with another Spark app, put into S3, put into an Elasticsearch, put into a Redis, give it to data science. Who cares? Give it to everybody. It's all available at that point, and your app just kind of keeps on spinning. So the second part here is basically saying, given that we have metric ags, And we have a different process that's actually writing that data to either Elasticsearch or Redis or S3. We can then say, let's take a look at the same data that's coming in the same aggregation window at the same time, and basically compose a view of the difference, basically what's the delta, or what's anomalous about the shape of this current data and the statistics in this current frame versus what we had historically. If you think about like anomaly detection, typically you're looking at a certain number of windows back. So if you have a way of basically doing like, sub 100 millisecond query to get an unlimited size window to basically, look back against, then that's really easy for saying, okay, we don't know what we're looking for, but we know we have key performance metrics. Therefore, if we take the key performance metrics and we're taking a look at the stream in real time, and we have a historic window of data to look over, then all you're doing is basically saying, you're going to use like a Pearson correlation, you're going to do other distance functions, you could do, basically auto regression. It doesn't really matter. It's all kind of available for you at that point. So you can basically process the trends, and then you can emit those events. If you remember the keynote from yesterday, Apple was talking about how they actually handled a kind of intrusion detection. So if you know what a certain threat might look like, what that model might look like, then you could also apply the same kind of pipeline to do the same sort of thing with intrusion detection. It's pretty much kind of more of a generic pipeline for doing anything that you want to actually do. So if you were to build this, here's the steps to do it. If you wanted to, you could basically take Spark 2.3.1 or wait for Spark 2.4 for continuous mode to actually be working a little bit better. And then take the continuous stream of data. You could use like a Guava loading cache for like what a dimensional hash would look like for a specific window. So you don't have to keep on going back to your data source. And basically just feed everything through a map against the actual data. If you flat map it and it's not actually anomalous, then just throw it away. And then your data stream would literally just be the actual events that are interesting. So you don't know yet if it's a problem, but you also know that you probably don't have time to look at every individual event in a gigantic system that's globally available. So if you can basically bubble up certain problems or say, this dimensional hash is interesting because it's basically firing a ton of events. What's interesting about this hash? Oh, it's a certain carrier over a certain route, and there's certain deviations that don't seem normal. Or if you think about like the state of a specific call, you might never get to the point where a call is completed. If a call never completes, what happened? Is it getting dropped? Is there something else there? So you can actually take basically like an enum value for a call state and take a look at the way that the call state enum values change over time. You can use a bit vector to see whether or not you actually make it from initialization to an end of a call. If the bit vector never gets back to 0, it's an anomaly. There's a lot of different things you could use this for. But basically, take your data, investigate, discover, and then emit downstream. So, in conclusion, because we have 2 minutes, discovering trends in massive data sets doesn't come for free. But if you take a look at the core properties and principles of like what we talked about for valuable data, honest data, accurate data, follow ideologies for that data, follow the patterns that I showed you, then you can find interesting patterns in your data, and that's it. So, thank you guys. Before I open it up for questions, I wanted to thank Rohit, who's in the front row. He's on my team at Twilio. I also want to thank Marek Radomski, who actually wrote the expression encoder for protobuf. That was a nightmare to get it to actually work without basically doing core dumps. Once you get to the point where there's no longer core dumps, it's actually really fun to work with it. But getting to the point where you can actually create like a row from protobuf was actually super challenging. So the credit goes out to Marek for actually doing that. Cool, that's it. So thank you guys. Any questions? Awesome, cool, thank you.